NCKU now. So yeah, as mentioned, so I'm going to talk about quantum imaging with it, which is my domain of research. And well, so maybe you would have understood that on this spectrum of trying to develop quantum technologies, so the one I practice, quantum imaging, is more dealing with the quantum sensing side of this, well, big attempt at developing new quantum technology. So really using quantum behaviors to have some form of improvement. So the type of improvement that we are targeting in quantum imaging is obviously, well, I mean, there are two kinds of things that we can hope to do with quantum imaging. And what I'm going to do throughout this talk is to try to show you different examples of research and, well, mainly realization I've been involved in, but one realization I'll try to flag it that I've not been involved in, but I think it's beautiful, so I wanted still to talk about it. So there are two things that we can do with quantum imaging. The first and most obvious is definitely linked to this quantum sensing side of quantum technology. And it is to try to improve imaging. To basically improve the quality of images. So that can be resolution, that can be noise, as we will see, and yeah, just get a better image by using quantum state of light. And the second part will try to harness the very high dimensionality that we get in imaging to have high dimensional potentially realization of the quantum information protocol. So, I mean, it has not been done yet, but it's, well, I mean, not in a very, I would say, efficient way. But that's certainly people have in mind in this field. So, I mean, you may have heard the saying that says, an image is worth 1,000 of words, and clearly, yes, like in an image, we can have a lot of information. And in fact, in the transverse dimensions of a light beam and in an image, you have a very high dimensionality that you can potentially access in addition to other domains like polarization, time beam, to basically increase potentially your, well, the Hilbert space of the state that you are, the dimension of the Hilbert space of the state that you are using and harnessing. So the problem in this context is that if you want to do quantum imaging, I'm going to try to convince you that, and certainly that's what I've been doing in the past, that we want actually to use, well, it seems obvious, but those cameras need to be available. We want to use camera to perform the measurement. So the reason for that is that, well, we want to access this quite, maybe I can, yeah, try to find a pointer. Yeah, you want to access this high dimensionality. But the problem is that the simplest thing you will do in quantum imaging, and well, more generally in quantum optics, is to detect correlations between photons. If you want to do that in images, well, now you've got two beams and two sides, two photons. And for, well, if you've got only a classical state, only one image, and one photon within this image, what you will have to do is to, if you don't have a camera, is to scan the whole image in each positions, in each transverse position of your light beam. Now, if you move to detecting a two-parted quantum state, well, you want to characterize your full correlation function and your full conditional probability distribution to find one photon conditionally on the other, which means that now you don't have one image, but you have two images, two beams, two sides. And for each the first detector. So you see that it's something that will be very slow because you need to raster scan a lot of points. So it's a quadratic in terms of the number of pixels that you want to have in your image. But if you can have a camera, actually, you will reduce quite a lot your acquisition time, but also you will increase the efficiency of your, well, protocol or of your detection of the quantum feature that you are, for example, entanglement, as we will see later. So you will increase this efficiency. And for some of the schemes, especially in metrology, the efficiency is really important. When you want to improve the sensitivity of a scheme, an imaging scheme, for example, then the efficiency really matters. So I'm talking about the heralding efficiency. So if you detect one photon, what is the probability that you've detected the other photon? And the problem, if you've got point-like detections, you put one detector on one side and you scan the whole image, when most of the time you will miss the twin photons, the photon that is correlated to the one that you are measuring in positive one. So therefore, having cameras that are able to detect single photons is really what you want to find and what you want to use in quantum imaging. And that's what we've been trying to do, I mean, in the past probably decades, from what I'm going to show you. So yeah, it leads to fast acquisitions, but as well to quite potentially efficient acquisitions that will allow you to do things that you could not with point-like detection. So just as an example, this is probably the first realization of quantum imaging. While it's quantum and they were using quantum light, but it can be done classically. And it's what they called ghost imaging. But nevertheless, it's one of the first realizations in this domain of quantum imaging. They were using quantum correlations here to detect an image. And as you see, they were, so those cameras that are able to detect single photons at the time were not available. So they had to take conventional SPADs, so avalanche photodiodes that are able to detect single photons. And they had to scan the images here to get their correlations and perform their scheme. But so what I'm going to show you are realizations that now use cameras. So I'm going to talk about two camera technologies that I've certainly used in the past. So there are new cameras, and we are hopeful to use them in the future, and I'm hopeful to use those in Taiwan. But I'm going to here focus on two main technologies that are, well, I'm going to go through, but that are EMCCD, so electron-multiplying charge-coupled device, and intensified cameras, we will see. So they have different characteristics for different purpose, and we will use them in different schemes. So I'll try to explain where we can use which one. So that's the plan of this talk. I've separated that in three parts, actually. So the first part, I'll talk about a few a more fundamental realization of detection of entanglement in images. So I should say those realizations have a lot of loopholes. So I should pick carefully my words, and it's like more detection of entanglement features in images. So I'm going to first talk about imaging of EPR features. So EPR stands for Einstein-Podolsky Rosen feature. Well, I mean, I'll explain a bit for those of you that are not familiar what it means. And then a more recent realization that I've done when I was in the University of Glasgow about detecting the violation of a Bell inequality in images. attempt at well developing quantum technologies, and where we try really to basically improve, use quantum state of light and use the correlations I'm going to talk about in the first part to perform a better imaging than you could potentially classically. So I'll focus, the first realization is the one that was done by an Italian team. It's a beautiful realization. I'll try to talk about it. And the second realization, quantum illumination protocol, is what I've done as well at the University of Glasgow. And then the last part, I think I consider that as opening a bit to, well, this future hope that we can use imaging to perform more quantum information protocols. So use this type of entanglement in a way that we could potentially perform more complex quantum information protocol. And the first step of that was, as I'm going to show you, to demonstrate Hongu-Mendel interference in imaging, so in a fully spatially resolved way with many entanglement modes, with a state that has a very high Schmidt number. Yeah, so that's the plan for today. So I'm going to talk about different realizations. So, but first, here I introduce the source and the entangled state. I mean, how we generate the entangled states that basically we will then use in each of the realizations I'm going to talk about today. So the source that we use is the SPDC. SPDC stands for spontaneous parametric down conversion. So spontaneous parametric down conversion is a nonlinear optics process through which we can actually well down convert the frequency of a light beam. So what we have here is a crystal that is transparent, and that is a nonlinear crystal. Within this crystal, well, we pump this crystal with a UV beam that is coming here. Those photons within the UV beam will have a chance to actually interact in a nonlinear way with the material that composes this crystal. So usually we use what we call a BBO crystal. And through this nonlinear interaction, some of these UV photons will be basically down converted, so broken into two infrared photons. So we have to satisfy the conservation of the energy. So we start with ultraviolet photons at 355 nanometers, and then we generate two photons at 710 nanometers. So that's satisfying the conservation of the energy. So what we have after this crystal is, well, a lot of remaining UV light, but some of those photons, so it's a really inefficient conversion, but still some of those photons have been converted into, so from one UV beam into two UV beams that are propagating at an angle separated by about, I think, 3 degrees. So what you see here and here are those two beams, well, the photons that are propagating in those two beams. And it turns out that, as we will see later, those photons are, in fact, they are so not only correlated in position and momentum, but these correlations actually in both position and momentum means that they are entangled. Okay, so here I'll just show you that. So from this crystal, what you can do, the first step in quantum imaging, as you will do, is to image. So take an imaging system. So basically just a lens and a camera after this lens to image a plane, well, within each one of these optical axes. So you take actually two systems, well, two lenses and two cameras, and you put each one of these systems along each one of the two beams, the two entangled beams that you've generated through this nonlinear process. What you do then is that you're trying to image a plane that is within this crystal. And if you do that, what you are doing is really detecting the positions of these photons, these infrared photons that you have here. So that's what we show here. If you do that, you will find that each photons within their own beam will always arrive at correlated position. By that I mean is that they will always arrive. So you detect one photon on the first camera and one photon on the other camera, but they arrive on the same pixel, so compared to the center of each one of their beams. So this is due to the fact that actually this interaction, this nonlinear interaction within this crystal is happening locally. And those two photons are basically generated in, well, a neighboring transverse position, which is where the UV photon was annihilated to generate those two photons. So really, the two photons are generated in a neighboring position, not exactly the same position. We still have an uncertainty, as we will see later, on their position, but nevertheless, they are correlated in position. Now, if you were to modify here and here your imaging system to now no longer image an inner plane of this crystal, but now, well, a Fourier plane of this crystal, what you will measure really are the angle of propagation of each of those photons. And this angle of propagation, because we select only one precise wavelength and frequency, it is directly giving you the transverse momentum of momenta of these photons. And if you do so now, you will no longer detect correlated arrival of those photons, but anti-correlations of those photons. So if you detect on one camera the first photon at position at the pixel plus 100, you'll detect the other one at the pixel minus 100, because they are, well, the momenta are anti-correlated, and it's due to some conservation of the momenta in this nonlinear process that is happening in the crystal. But nevertheless, this property of those photons to be both correlated in position and anti-correlated in position in momentum is exactly actually EPR type entanglement, and you can use that for EPR steering. I'm going to show that to you just now. So I'm going to talk about the first realization. So this one has been done at the FEMTO-ST Institute in France, and it was during my PhD actually. So we started to use these EMCCD cameras. So those cameras are just, so the sensor is a conventional CCD sensor. So you've got photons incoming onto your sensor, and you generate photoelectrons within this photosensitive sensor. The only difference that you have here with conventional CCD is that after the serial register, where you read the charges in this direction, and then they are shifted to be read and converted into a digital signal. Before this conversion and before having this output amplifier, you've got a serial gain register that is here. What you do with those photoelectrons that are read here is that you accelerate this in a strong, under a very strong voltage. And then through impact ionization, you will basically multiply these photoelectrons that are here. So the gain in these cameras can be up to, I think, 1,000. Maybe in the more recent model, it can go to 5,000. But nevertheless, this process is fully stochastic. So what you get out of these cameras is grayscale images. But as you can see here it's a line of an image where we will expect to, in each of these pixels that you see here, we will expect to have only 0 or 1 photon because the light is really dim in coming onto this sensor. Here you see that you've got wildly different grayscale values for the peaks. And it is due to the fact that, well, the gain is, I mean, this process is stochastic. Therefore, what we need to do to get photocounting images is to apply a threshold. We know all the noises, and therefore we can guess, well, I mean, we can deduce what will be the best grayscale level threshold. So above this threshold, we consider that one photon, if one pixel is lit above this threshold, one photon was detected, and below this threshold, no photons were detected. We set the threshold just given the characterization that we've made of all the noises of the camera to maximize this guess on, well, was a photon detected or not on this particular pixel. Yeah, so we minimize the error that we can do. So we've got, I mean, many type of process that we can use. Some are Bayesian estimations of this threshold. But nevertheless, what we get after this thresholding, so we start with, so those are the raw images that we get out of the camera in grayscale levels. And we binarize and we get this type of binary images. So this is an image, an experimental image of one of those two beams, so SPDC beams that I've showed you before. So what we have here in this part of the image is, well, the actual beam. But you see here in the corner of the image that we still have a lot of noise. And it's one of, so here we will expect to have no light. So the detection that we have are false detections of photons that are mainly due to the clock-induced charge in this CCD camera. So that's one of the drawbacks of this camera. They are very efficient. So the detection efficiency is up to, after thresholding, up to 70%. It is useful for some of the applications. Inequality, we need to use another type of camera. Nevertheless, we can still work with this photon counting camera to detect EPR features, and that's what I'm going to show you. So that's the scheme that we use to test. So Einstein-Polotski, Rosen, I should say, entanglement, but the feature of entanglement in images. So what we have are now two schemes, well, two setups. The only difference between those two setups are the position of the lenses that you've got on each side and the position, well, along the z-axis, the propagation direction of the light of this camera. So one setup corresponds to the measuring here, what we call the far field. So that's the measurement of the momenta of the photons. And the other measurement is measuring the position of the photons. So as I said before, what you do here is that you set up your optical systems in both arms here to image an inner plane of this crystal that you get here. So here, well, I should start from the beginning. So here you've got the crystal, the same crystal I was talking to you about before. You pump it with the UV pump here, and then you generate those two beams. Well, we show those in different colors, but they are really at the same frequency, so 710 nanometers. And then you use two mirrors to send those two beams that are separated in angular, that have an angular separation in their propagation, and to those two cameras. And each of those two beams contain, well, the entangled photons. So here you measure their position. In another setup, you measure their momenta. And the way you do that is by just acquiring with this EMCCD well, these images that you've got here. And then you analyze those images in a way I'm going to talk quickly about to detect the correlations of the position and momentum within these images, and ultimately to detect the entanglement feature within these images. So the criterion we use to well, demonstrate this Einstein-Polotski Rosen type of entanglement is a criterion that was derived actually fairly recently by Reid at the University, Margaret Reid at the University of Queensland, I think, in Australia. And the way we do that is that we evaluate two variances. One that corresponds to the position of the two photons. So what we do is variance of position of photon 1 minus the position of photon 2 times variance of position momentum of photon 1 plus momentum of photon 2. And you can show that if the quantum state that you are analyzing here is verifying, well, is below this Heisenberg limit that you have here for this uncertainty, So it's not violating the Heisenberg limit, but because it's a quantity here established for 2 photons. But still, if you go below this Heisenberg limit, it means that you cannot explain the experimental results by so-called local hidden state. And therefore, it means that you can potentially use this state to perform some EPR steering. In this case, it's a particular form of EPR steering because things are symmetric. Oh, sorry for that. Things are symmetric between both sides. And therefore, you can steer equally both ways. Yeah, sorry again. So, well, I hope, can you actually hear me? I hope it's not you calling, actually. Yes, we can hear you. Sure. Okay, sorry, I had it up. Okay, sorry. Because I don't have feedback, so it's hard for me to know. Thanks. So I was saying, yeah, so we want to use this criterion. So we just want to use these images to establish, well, to evaluate those variances in these images to evaluate this criterion. So what we have here is directly, well, so that's the conditional probability distribution of those correlations in both the near field and the far field. And basically what we can do is to do that in both the X and Y dimension of the images. So we'll have 2 inequalities actually to test in both X, as you can see here, and we'll have an inequality in Y. So in both X and Y, what we get are a correlation in positions. And in the far field, in the momenta, we get this anti-correlation. So as I was saying, if you detect photon 1 at position 100 on pixel 100, you detect photon 2 at position minus 100. And actually, the width here along this line of those quantity is linked to the variance that you have here. This type of correlation peak on which we can evaluate the width, so those 2 variances in both X and Y dimensions. And we can basically test for this variance product here to see if we've got EPR entanglement within those images. So I should mention that, well, what we get, the way we get those 2 peaks here is that we take those images coming from each camera. So we just apply a numerical cross-correlation between those images, and we sum those cross-correlations to perform like a temporal average still of this figure. And I think we had a lot of like over 1,000 frames here to get this correlation peak. Nevertheless, using these features, we are able to show that, well, we go below the Heisenberg limit, and therefore we have this EPR steering that is happening in the quantum state here. Now we wanted to show in next demonstration that we were able to use this scheme and the fact that we are using cameras, and that therefore we are performing very highly parallel measurements here on each pixels of the frame. We are actually doing a measurement of the position of the photons and the momenta in the far field. And therefore, we wanted to show that by using cameras, we had a way to perform this demonstration very efficiently, so that now we could perform this demonstration in single frames. So just acquiring, well, 2 frames in both position and momentum, cross-correlate those 2 frames, and get a correlation peak that you can see here, and just evaluate the presence of entanglement only on those single frames. And we were able to, well, show that consistently on single frames, we were obtaining this feature that was going below the Heisenberg limit, just demonstrating in those single frames. And for a very short acquisition time, I think it was about 100 milliseconds, demonstrating this presence of entanglement. Okay, so now that's for EPR entanglement. Now we wanted to go, so that's what we wanted to do in the University of Glasgow now. We wanted to go a step further. So if you know the hierarchy of entanglement, so the entanglement is the most general form that is defined by non-separability of a quantum state. But a stricter form of entanglement is EPR steering. But a truly non-local form of entanglement is an even more strict form of entanglement, is Bell non-locality. And what we wanted to do after this earliest demonstration is to show that we could actually demonstrate the violation of a Bell inequality and therefore some type of Bell type entanglement in images still. So that's what we've done. So as I mentioned before, we cannot use for that EMCCDs because they are too noisy. So we used a different type of cameras that are called intensified cameras. And the way they work is that we have here just a conventional CCD, and the amplification stage that was happening before in the chip when we were reading the charge is now happening in a so-called image intensifier that you've got in front of the camera. So a photon is antecedent on the photocathode here, and we generate an electron that is then multiplied in a microchannel plate here. So you've got one photon incoming, many photons, many electrons here, and we convert back those many electrons into a flash of light on a phosphor screen here. And this flash of light is easily detectable, goes like above the noise threshold of this camera. So those cameras will exhibit a lower noise, and especially because you can gate these microchannel plates with very short gates. But the drawback of this is that this conversion here that is happening on the photocathode is really inefficient. So the efficiency will be quite poor, but you'll have a quite low noise with these cameras. So the way we did this demonstration of, well, the test of a Bell inequality, usually Bell inequality are tested on this block sphere, where we've got here polarization of the photons. You've got two photons, and on which side you've got a block sphere on which you test the polarization of one photon. We wanted to do that in images, so with dealing with spatial features. And one spatial feature that can map onto this block sphere is actually the OAM, so orbital angular momentum of light. So those features are just, you can understand this as just filtering your light beam that is spatially extended with holograms. You can have holograms that looks like this, so that's the distribution of the hologram, or you can have holograms that just looks like a phase step, a pi phase steps, with a certain orientation in the space here, with a certain axis of separation. So the axis is here. And it turns out that these objects, so these pi phase steps, are exactly on this block sphere, exactly equivalent. So they are sitting on the equator of the block sphere. And you can understand these phase filters that are in space exactly in the same way as you would use a polarizer on this polarization block sphere with a certain orientation. So the orientation in space of your phase step is exactly the orientation of your polarizer that you would have in a conventional test, Bell test, polarization-based test of a Bell inequality. So we were basically playing with this OAM space here as an Hilbert space. So it's still two-dimensional, but we can use this very high dimensionality to perform this in a single image to have highly parallel measurements on this Bell state. So that's the setup we were using. So I'm not going to enter into too much detail because I don't have the time for this, I think. But what we use here is, well, so we've got the same state here. We've got the two beams that contain the two entangled photons. And what we have here are SLMs, so spatial light modulators. You can really understand those SLMs as basically programmable hologram. So we can decide with the computer what we want to, the kind of phase filter that we can impose onto these holograms, onto these SLMs. And then we detect on one side with the camera the photons, and on the other side we basically trigger this camera conditionally on the detection of a photon after this phase filter. So on one side we have exactly what I was showing you, so those phase filters, those pi phase steps, that corresponds to different orientation of the polarization in conventional test. But on the other side, what we image actually is a phase circle. Along the perimeter here of this phase circle, what we have actually is locally a continuum of those type of objects, so those pi phase steps with different orientation that are tangent to the phase circle. So it means that if you consider one point on this phase object and a certain choice of phase filter that you can put here, what you will have is, for example, if you are here, it's equivalent to having on one side a polarization, a polarizer like that, and in the other side, a polarizer like that. And that's all you need to perform a Bell state. I mean, you need to have Bell entanglement, but it turns out that with this type of state, we do have Bell entanglement incoming onto those projection basis. So what happened here is really a projection in both sides that is composed on one side of this SLM plus this detector and this SLM plus this detector on the other side. So I'm not going to enter into all the technical detail of this demonstration, but nevertheless, we were able to acquire with this setup and through this type of projection an image of this phase circle as remotely interfered, well, remotely filtered by these phase filters. And we are able, just with this email to, this image to test for a Bell inequality. So I should mention that these images are not intensity images, but that's directly correlation images that we get from this camera, just because the correlations are obtained through the fact that, well, the camera is triggered conditionally will only acquire when first photon has been detected on this side. So those images are already correlation images. We use these images, so we just analyze along those four circles that are here, that corresponds to the display of those four phase filters. And we just unfold here the correlation that we get along each one of these four phase filters. And we get this type of sine squared looking correlation functions that we hope to see actually in a test of a Bell inequality. And if we test now for the S value that corresponds to the violation, the test of this Bell inequality, we find that we get a value that is above 2 for these correlations that were detected here. And above 2 means a non-local type behavior. Therefore, with this setup, we were able to demonstrate well, the violation of a Bell inequality, and therefore the presence of entanglement features in these images. Okay, maybe I'm going to be out of time soon, so I'm going to try to pass quickly on the other part of this talk. So this is the part where I talk about now. So I've talked about making some fundamental demonstration of the quantumness of the state of light we generate in images. Now, how can we use these images to perform basically a better imaging scheme? So the first type of realization along those lines was performed actually so I was not involved in that research, but I think it's a beautiful research. So it was done by the team of Marco Genovese in Italy, so in the University of Turin. So what they try to improve in images is get images that were said to be subshot noise. So in quantum optics in imaging, each images that you acquire will noise is really due to the fact that light is composed of single particle of photons, single particle of light. And therefore, if you are trying to acquire an image of a scene, what you will see first is a few photons arriving. And well, if you've got only a few photons, this image that you are acquiring will be a poor representation of the ground truth of what your image should be. So the ground truth will be here, for example. And this poor ability to basically describe this ground truth, we can characterize that by a so-called shot noise that we can define. And what they were trying to do is to use quantum state of light to perform the acquisition of an image that is better than the fundamental shot noise limit, basically. So what they did is that they were using the same type of state that I've talked to you about, that exhibit the type of entanglement we've demonstrated just before. But they were using a conventional camera that works in a very different way. So what they have here is a camera that is no longer acquiring single photons, but that are acquiring a lot of photons. So per pixels, you'll have a lot of photons, so about 1,000, I think. But you will still see this shot noise. You will still see this type of noise in your image due to the fact that, well, you don't have an infinite number of photons in your image. So you still have a certain amount of shot noise in your image. But the fact is that because you still have correlations, photon correlations into between this part of the image and this part of the image that corresponds to the two beams that are correlated, if you've got one photon incoming in this pixel, you'll have a photon as well incoming into the other pixels. And therefore, both sides of the image will experience the shot noise, but each pixel within this image will actually experience the same shot noise. So if you've got a perfectly ideal scheme, the number of photons you detect in one of the pixel will be random and follow this shot noise. But you know that you'll detect exactly the same number in the other side. And you can use this, the fact that you are measuring on the other side the number of photons, to basically subtract the noise that you have in your image. So one of those two beams is sent onto a slightly absorbing object that looks like a pie here. And then they detect the number of photons after this object. They subtract B, image B to A. And by just simply doing this subtraction, they are able to subtract some of this shot noise. So that's what you see here. Here's the classical image. So directly the intensity image that you have after the object. And by just subtracting B, they are able to get those quantum images that exhibit less of this noise that you have here. Okay, another thing that you can improve upon in using this type of correlation is through a so-called quantum illumination protocol. So that's what we have here. So what we really try to do here is to get rid of some of the noise. But this noise now is not this fundamental shot noise, but this noise is basically an environmental background noise that comes from the fact that the scene that you are trying to observe is potentially in a noisy environment. So what you see here, you're trying to observe this cube. What you will do classically is that you will send some light onto this object, and that you will detect backscatter light from this object. But because this object is in a noisy environment, the problem is that sometimes, even if the object is not here, you will detect some backscatter light, and you will not be able to know if this light that you detect here is coming from an object that is here or is coming from the background. Okay. Okay, I'm sorry. Can I just go back. I've got ready to go to. I'm so sorry. I'll come back in 2 minutes. Okay, so, sorry. I'm sorry. I think I drank too much coffee this morning, and I really had to go to the toilet. So I'll finish quite quickly. So can you please tell me? So should I keep like 5 minutes for the questions, or do questions go after 11?
It's fine. We could ask question at 11.
Okay. So I'll try to finish in 10 minutes. Yeah, sorry for that again. So what I was telling you is that, so classically we've got this type of schemes where we cannot really distinguish between a light that comes from the environment and a light that is backscattered from originating from your actual source. But what you can do is to use correlations, and in particular quantum correlations, to actually detect a signature of your correlation within this backscatter light, which means that basically the backscatter light will be correlated to a reference light that you are keeping here, but the environmental noise, however, will not be correlated to this reference that you keep here. And therefore, by detecting the signature of this correlation between this reference and the light that you receive from the scene that you are trying to observe, you can really distinguish what comes from the scene of interest and that you are illuminating, and the noisy environment source of noise. So this scheme was introduced theoretically by Seth Lloyd in 2008. And we were trying to implement that in the context of imaging. So the way we basically kind of simulate this scheme is through this realization. So what we have here is the entangled source that we are using throughout all this talk. We've got those two beams that are quantum entangled in the space. We keep one beam as reference in this part of the image. And we send the other beam through an object here looking like a bird that we are trying to observe. What we do then is that we superimpose onto the sensor and onto this object, we superimpose the noise, actually, that is just thermal light that has the property to actually be really noisy and really hard to deal with when you want to get rid of it. And we just shape it as a cage, just to show that then when we use these correlations to detect what part of the image here that is detected on this side is correlated to the reference and quantumly correlated to the reference, we are actually able to remove the noise that is coming here from this parasitic light. And we get basically better image of the object here. So we get a bird that appears to be free of this noisy cage that is here. So those are the actually earlier images that we obtain. So as you can see here, I should mention what I call classical image here is directly the intensity, so the light intensity that you detect here. And here in this light intensity, well, you cannot, if you do not make any presupposition on how this noise looks, you cannot, and how the image that you are trying to observe looks like, you cannot remove this noise, basically, in this intensity image. And the quantum image is basically correlating this part of the image to this part of the image to keep only, potentially, the quantum light. Okay, so we get these images that looks better, but actually quite recently, we've improved upon the estimator that we are using for this improved image. By using both quantum and classical informations in these images, we are able to actually get fully rid of the noise that is here. So you can see here, for example, that we've got a very high noise compared to the level of intensity of the bird, but we can actually still see the bird here. Okay, and well, I've got less than 10 minutes, so I'm really gonna move very quickly to this last realization. So what I've showed you up to now was, well, fundamental demonstrations, then examples where we can use this type of quantum imaging to improve images. And then, so that's also a fundamental demonstration, but for me, I think that opens the many paths for this domain, I think, of quantum imaging. And so this realization is what I've done. So I was in Glasgow, but it was in collaboration with people in France. And what we've tried to do is to demonstrate the Hongu-Mandel type of interference. So Hongu-Mandel interference is really a two-photon interference. So the way it works is that you've got a beam splitter here, and you've got two beams of light that contains each single photon. Those two single photons usually are in single modes spatially, and you superimpose those spatial modes, you superimpose them temporally and in a frequency as well, so that you make those two photons that are incoming onto your beam splitter indistinguishable. In a way that after the beam splitter, if you detect a photon, you cannot say if it comes from this input of the beam splitter or from this input of the beam splitter. So classically, what you will expect to see are 4 possible cases, and you will certainly hope that half of the time, well, the two photons that are coming onto the input of your beam splitter exit the beam splitter by just each photons take a random exit, which means that half of the time, the two photons will exit by different outputs, and half of the time they will take the same output. But quantumly, what happens is that actually you've got an interference between the two wave functions corresponding to those two photons, which means that those two cases that you see here will basically cancel each other through this interference. And what you will always see if your two photons are perfectly indistinguishable is that the two photons will exit the same, will exit this beam splitter always together by the same output. So that's what you see here and here. Which means that now if you've got two detectors, one on each of the outputs, you will see a loss in correlations because you do not detect anymore photon correlations between those two detectors because the two photons always are detected on the same side. What we wanted to do is to do that in the context of imaging. So harnessing this very high dimensional entanglement that we have in the space domain, and this very high Schmidt number type of entanglement. So this is high dimensionality. So that's the scheme we use. So we still have, well, the VBO crystal, two beams here and here. We send those two beams onto a beam splitter. So those two beams have now not a single spatial mode, but many entanglement modes. And we try as best as we can to superpose all these entanglement modes onto this beam splitter. And we then detect within two camera images these two photons that are outputting the beam splitter. So the difference that we have before, compared to before, is that now we've got some spatial resolution, and we can not only detect the correlation between, well, camera 1 and camera 2, but as well photon correlations within a single image, so within a single camera. So we can detect those two photons that are actually taking the same output. So we define three functions, one that is a tree correlation function, one that is C12, so correlations between two outputs, C11, correlation between one output with itself, and C22, correlation between one image at camera 2 with itself. And what we see here is that from the top images that are correlation images to the bottom correlation images, we switch from two photons that have orthogonal polarization and are therefore distinguishable, Ongu model interference not happening, to VV, so the two polarization of the two photons are the same, and they are therefore indistinguishable. And what we see is what we will expect, so a loss here in the correlations between the two outputs, and an increase of the correlations between within a single output, thus demonstrating the presence of this Ongu model phenomenon. So I'm going to finish soon, but I think that's one of the probably most important results of this demonstration, is that what you can do here, I think for the first time, is that you can have access at actually a map, a spatial map within your beams of this Ongu model phenomenon happening. So you can take an image of this Ongu model phenomenon. So here again, you switch from HV to VV, so distinguishable to indistinguishable. And you can see here, so this is C12, so correlations between those two cameras, so between the two outputs of the beam splitter. And you see the loss of correlations between this image and this image. And you can even see in a spatially resolved way where actually you have a very high Ongu model phenomenon happening, and where, because probably you've got some aberrations in your imaging system, where it's not happening as well as in other parts of the images. So you can see really this very high dimensional entanglement coalescing and well, verifying this Ongu model phenomenon. And we certainly hope that we can build from this result in the future and do things that are more and more complex, harnessing this very high dimensionality that we have in imaging, potentially for quantum information protocol. So just to conclude very quickly, I just want to mention, so I've talked about mainly two types of cameras throughout this talk. And we are certainly hopeful, and I am hopeful that in NCKU now I'm going to be able to use potentially the better type of cameras that are in development. Those are SPAD arrays and also SNSPD arrays that we've seen starting to develop. So SNSPDs are those superconducting nanowires that are very much the detector of choice in quantum optics. And we have seen some people putting a very small number of those in an array, trying to build a camera. So it's very exciting for the future development of quantum imaging. Okay, well, with that, my time is up, and I thank you for your attention.
Thank you. And is there any question from the audience?
So if I want to ask question regarding that.
Okay, you can go ahead and ask.
Thanks. You can come with this.
Hello, can you hear me?
Yeah, I can hear you.
Thanks for the great talk. So I'm just curious about the noise of the image, because this image is imaging the photon. So there should be a lot of black body radiation photon. So I'm just curious about if we just put the whole system into a big fridge, will improve the image quality.
Yeah, so I think because we are working here in the visible domain, so well, I mean, it's I said it's those photons are infrared, but it's like really near infrared at 7-10 nanometers. Actually, the black body radiation is not so much of a problem. Well, it is certainly what is a problem is that, well, we have to cool these cameras, and they are definitely water cooled. They are put at minus 100 degrees Celsius in order to get this type of images. But it's true that we still have a lot of noise that is technical camera noise. But definitely, I mean, one of the targets that could be aimed to develop, like actually quantum technology with this type of demonstration, where we do a quantum information, quantum illumination protocol, for example, is that this noisy baths could be actually, if we shift to other wavelength, could actually be well, black body radiation from the environment. And certainly we hope that actually using this type of schemes, we will still detect this noise on the images that are here just symbolized by the cage. But using these correlations, we could get rid of this black body radiation actually. Yeah.
Yeah. Okay. Thanks.
You're welcome. And yeah, so maybe I should mention on the noise that, well, obviously I showed you this image where we have a lot of noise here. But when we switched from EMCCD to ICCDs, they are really less noisy. And this image that we get, the dark that we get here, is not background subtracted at all. So here the dark is a real dark. We do not have any photons detected here. And we can do that because we are using an ICCD.
And here we have another question.
Okay, thank you for your nice talk. Maybe I just curious about the fundamental question. How's the spatial map reflects the correlation? I mean, is the why the correlation can be read out from the spatial map? Is there any fundamental property of these correlated photons so that you can see that?
So, sorry, I'm not sure to understand the word that you're using. So please, could you ask again the question?
You cannot hear the voice, or you don't understand my question?
Yes, there is, I think, one of the key words that I didn't get. So you're asking about those quantum correlations in the space, and you're asking how can we use those, or?
I mean, why the correlation can be written in the map, in the spatial. Because
sorry,
the photon, discuss, or you are studying the photon, single photon, right? Single photon correlated with another single photon, so you treat them as the wave package or anything, so that you can find the spatial overlap reflecting their correlation. Is that the reason?
Yeah, so I mean, so to me, these positions, they are simply just a variable. So you can basically, when you detect a photon at a precise position, it means that your wave function has collapsed onto this precise position. In the same way as, for example, in polarization, well, if you come with a photon that is on a superposition of two polarization, if you just put simply, well, a polarization beam splitter, for example, then by measuring in which path of the polarization beam splitter your photon is detected, you'll have basically projected this superposed wave function of your photons onto a certain polarization. Here, what we have is a superposition of the photons on many potential positions and later momentum. And when you put your camera, what you're really doing is trying to measure this position and to collapse your wave function at a precise position. And then the entanglement that you have is really an entanglement between those variables. So those two sets of potential, superposition of positions in your both sides. I'm not sure if it answers exactly the questions. I hope so.
So, to know the entanglement, so basically the polarization is the key point, right? So you have to measure the polarization of each photon so that you find how they are correlated. Mm-hmm. So I'm asking further, is this a statistical derivation, or you can find just single photon and claim the result, or you have to do too many single photons to do the statistics?
Oh yeah. We don't do that on a single photon, so it's exactly the same as you would in polarization. I mean, you average over time in polarization. Here, what we can do is that we still have. So when I say we take single frames, we have only single frames, and we do not do a temporal average. But what we do is that we do a spatial average, if you will. So we use the fact that we've got many pixels and as well many photons detected in a single frame to do a spatial average, if you will. So we switch from temporal average in conventional quantum optics to do basically a spatial average. But we have many photons per image.
I see. Thank you. Sorry. Last question. Yeah. In your last part, you mentioned high dimensional stuff. So what's the high dimensional stuff you mean? In which high dimension? Because you are talking about photons, I'm not sure what you refer to.
So I mean, the way I can answer, if you're familiar with, I mean, I'm sure you're familiar with Schmidt modes, is that the Schmidt number is of the order of our quantum state. I mean, the measured Schmidt number here is about 5,000. So it means that's the dimensionality of the entanglement. That's so we suppose that the dimensionality of the entanglement is actually that we generate is even higher, but we are constrained by things like the pixel size to actually measure this dimensionality. So 5,000. Well, I mean, I can say it's above 5,000. So 5,000 modes of entanglement, Schmidt modes.
So, sorry. So you are saying to me, stay or some? Maybe I'm not familiar with that. So you are referring to spatial stay or?
Well, I'm referring to the Schmidt modes. So Schmidt modes are directly if you will, the modes of entanglement of your quantum state. So it's valid in any kind of Hilbert space, in any dimensions that you are trying to study. So you can define Schmidt modes on polarization states, but then you will be bounded by the fact that, well, you've got only two polarizations.
I see. Okay. Thank you.
You're welcome.
Another question.
Yeah, also regarding to your work about the Parametric, you design an optical experiment. So according to Cheslow's protocol, you need to have storage device to storage the idle signal. Is that true, or is that also happening in your experiment? Can you hear me?
Yeah, I mean, I can hear you, but I'm not sure to have understood again. I'm sorry for that. To understand again.
Okay. My question is that about the idle signal, because in Cheslow's protocol, you need to have an idle signal storage. Is that true, or did I misunderstand anything about that?
The idler signal.
Yeah. For the Swiss protocol, like the quantum information. When you perform the correlation, you need to have the correlation between idle signal and the target, the signal from the target, right?
Mm-hmm.
So you measure.
You're talking about. I'm sorry. Is it this one? So the quantum illumination.
Yeah, MVCT. Yeah. So do you need any equipment to store the idle signal or not?
No, I mean, in this case, we don't have any storage. So I'm not sure the version of the quantum information protocol that we are doing here is, I would say, the most fundamental version of the quantum illumination protocol. And there are certainly some people that have recently debated how can practically be this quantum information protocol be used? So I think their answer is that, especially in the very low photon regime, it still shows some advantages. And we are certainly working in that regimes. But there are certainly some drawbacks with, for example, using that protocol in LiDAR applications or things like that. So yeah, I'm not sure I understand perfectly the question, but I would say this might not be the most fundamental demonstration of quantum illumination protocol. What we definitely demonstrate is that, well, it's definitely a relative improvement compared to similar situations where we still reject some of the technical noise that we have here.
Thank you.
Is there any other question?
I have some questions here. And I guess maybe that will also help to clarify the discussions between Paul and some of the questions posed earlier. I think there might have been some confusion. Maybe they were thinking that it is the correlations in the polarization degrees of freedom that you were demonstrating, but I guess this is not the case. I guess you were actually demonstrating correlation in the spatial degrees of freedom of the photons. And maybe that's, I mean, one of the questions was about how these correlations actually became manifested when you do this position measurement. And well, I think that's simply because you are having photons that are correlated in the spatial degrees of freedom. Okay, so my question is actually related to exactly this slide. So in order for you to use this S parameter coming from the characterisation inequalities, so usually we think about measurements that have two possible outcomes if we wanted to apply these inequalities. So in your case, this two possible outcomes, is it related to just detection and no detection at a particular pixel?
So yeah, in this case, the two measurement. Well, no. So okay. So this case is exactly equivalent. So basically, what you will do in the most modern form of a polarization Bell test of an inequality is that you will have a polarization beam splitter that basically gives you two outputs, and then you get two detectors on each of those two outputs. But I think in the earliest demonstration that what they were using and what you can do actually is if you don't have a polarizing beam splitter, you will have a simple polarization filter, which means that you cannot measure at the same time H and V, but you will choose to measure H, have a single detector.
Not H, yes, H. Yes.
And well, sorry, H, and sorry, H first, and then you'll do a V measurement later in the time. If you don't have the optical apertures that can split H and V into two paths, basically. So that's exactly what we do. Here, those objects are, you can get those, understand those as simply, I mean, analogy, in this analogy with the polarization space. That is, well, that is H, so the one I'm showing here, and that is V. So basically, those two outcomes will be here and here. If
Okay, so
that makes sense.
do I understand it right by saying that you are just you know, binarizing the outcomes so that you say that they are either in the blue or in the yellow?
Yeah, well, and so the outcome says that they are either on this part of the image or on this part of the image. So
Okay.
if you get one photon, it will either come here or come here, depending on its polarization. Well, sorry, no, I mean, I should be careful, especially because of what you said just before, depending on their state in this
Right.
OEM space and not on their polarization. So I'm yeah, continuing the analogy too far, but yeah.
Okay. And maybe one other question that I have asked you already, maybe too many times. So the the difference between this near field and far field measurements.
Yeah, I mean, maybe sometimes we should really have a long talk about that, but I'm gonna do my best to explain it better.
So I mean, on these pictures, they look just the same, right? So I guess the pictures actually are not illustrating the difference.
Yeah, so they would, so they don't, I mean, so they look similar, but the difference is, really simply speaking, the distance. Well, maybe I can try to write it if I've got my pen works. Okay, let me. Yeah, so basically, the difference between this setup and this setup are this distance and this distance, and as well this distance and this distance. So just by changing this optical setup, we are able to make a different measurement. And basically, it's exactly the same as when you take a normal DSLR camera. You will basically rotate your lens to change your focusing, and you are observing a different plane. And in this case, in the near field case, what we do is that we are just taking a picture of a plane that is optically within this crystal. And in the far field, we take a picture of infinity, a plane that is at infinity. And at infinity, what you have is the angles of propagation of the photons, if you will, which corresponds to the momenta of the photons, is the transverse momenta.
I see. Okay. So it's just by adjusting the relative positions of this to place it either at a focal point or outside the focal point.
Yes. We change the focus of the camera, in fact.
I see. Okay. I see. Right. Great. Thanks. I think that clarifies.
Okay. Well, I'm happy to.
I'm good.
Okay.
Thanks.
Any questions? If not, let's thank Moreau again for this today's such a nice talk. So bye-bye.
Bye-bye.
Thank you.
Thank you.